Hello and welcome back to another episode of Getting into Good Oxide. Welcome back, Sydney.
Hey, Sebastian.
I hope you had a nice and recreational, can you say that, weekend?
Yeah, definitely. Summer's finally coming back a bit, so out enjoying the sun. It was good.
Yeah, unfortunately here, not so much yet, but this week I'm promised some sun. Can't wait. That should help getting stuff done, I guess, because you sit inside more, and judging by the contribution that I want to talk about first, I have to. That really does something. Like, people contribute more if it's bad weather time, even though it's a big world, and I have no idea whether that contributor had bad weather during the creation of this gold, but let's just assume it was. So before we continue with the usual stuff, I have to show, like, maybe actually show the commit here, because that is really, really new, just so that we see what changed and why it's so awesome. So this program is Dua, and if you use Dua and then a big folder, you'll see there is some counting going on, some enumeration here. And this enumeration was previously done by the following terrible mechanism, but I thought it's good enough because I didn't really know better and definitely thought, okay, it's quick and dirty and it works, so let's do that. So what happens here is that there's a counter, and that counter counts files, the count you've seen, this enumeration count. And it's in a shared atomic U size. So it can count quite a few files with that size, with 64-bit on most systems. And that shared U size is then, that U size is then shared, or that atomic count is then shared with a thread. And that thread simply sleeps for a second before it starts displaying the enumerating entries count using that shared count. And you see it's looping forever. It doesn't even bother to shut itself down, because as the process ends, it will shut down too. And then here, as we are counting on the main thread just increments that count. And this is how shared memory is used to let the count happen every 100 milliseconds. So that you don't spam too much. So that's a very fast way of doing things. Generally, transferring information through atomics is the fastest thing you can do. And it's safe, as we know. So it's really, really, this is why I did it in the first place. But can you tell what this suffers from? Like, not shutting down the thread, for instance, what this actually is.
I'm not sure, because you said the process ends after this action, right? So it shuts itself down.
But it's still a race condition, because there's no guarantee that the main thread goes down after. And also there's no guarantee that, after the main thread printed, it can very well happen that this thread gets another shot and prints the entries enumeration again. And that will then cause some overriding to happen and some weirdness. And that is rare, obviously, but it can happen. It's a race condition. And it can annoy.
So it's because those two threads or two loops are just desynchronized. They're just doing their own thing, basically. And
yes. And I knew that when I was writing it. I just thought, I don't want to think about how I communicate to this thread that it should shut down. So, you need some synchronization. And I didn't want to deal with it, I guess. And that also shows that synchronization or multi-thread programming is still kind of, an issue, in the sense that you have to think about it a bit more. And usually I use channels to communicate safely to threads, and then it's kind of okay to write it, but also I didn't feel like it. I felt it's too cumbersome and didn't want to do it. truth to be told, but that's it. It was me being lazy. I thought it's good enough. So the other disadvantage is that it uses this atomic U size, which unfortunately is not available in all platforms that Dua is compiled to. So there's a bunch of maintainers packages that compile it for different platforms, and this doesn't work everywhere. This is why there was this feature here to be able to turn that off. So that wasn't available everywhere. So those platforms who didn't support that, they could just turn off the capability and then this would work for them.
Okay.
So full of disadvantages, 2 disadvantages, building and that. So with that in mind, I mean, there isn't too much to remember, I think. There was the contributor who turned that into a throttle writer. And that throttle writer, it owns a trigger which is now an atomic bool. It uses shared ownership, kind of, with this arc, but it uses it in a way that, you know, this is what I want to talk about. This is the thing I learned. And it's this weird thing that you knew before, but you never used it for that, even though it's kind of obvious and in your face. But it's this 1 + 1 = 2, and you kind of know that, but also could never make it work for you. So here we come. So this throttle writer, let's see how it's used. I think that might make sense. So we have this here, this optional writer, because there might be a situation where there is no output like this, and some duration every 100 milliseconds in this case. And then we say we want to print some throttled progress here. And then we pass a function that is called only if we actually print something with the current amount of entries here. So that's then copied into, oh no, is that copied? No, it's not copied actually. It's just borrowed. Just a closure that borrows some state here. And it's evaluated immediately, right? So that's not evaluated later. It's just evaluated right then. And what it does is it uses this trigger as indicator, asking, may I print? And swaps false into it. So basically, if this trigger is true, this if condition will be met, and it will be allowed to write unthrottled, as it says. But then afterward, the trigger will be set to false. So it will never print afterwards. So somebody has to set this trigger to true again. Sometime later, ideally 100 milliseconds later. Okay, so that's how that works. And this unthrottled printing is literally just printing if it can. So if there is something stuck in that option, it prints. Okay. And the other uses this unthrottled print. So that's unconditional essentially. If you can print, then do, because that prints some special terminal escape code magic that clears the last line in a particular way. That wasn't there before, by the way. That's new. That's what was added. And I left it in there because it really makes the output a little bit nicer than it was before. So that's something cool that I also learned. You can do this. And now for the real cool deal. Like there could still be could there be a race condition like this? No. Because the only one who prints is the main thread. And there's no thread printing anymore. So whatever that thread does, if it still uses a thread, doesn't really, it can even live on. It can live on and keep setting this variable. Nobody cares, you know, it's okay. So that already, like this system already fixes the problem. So he uses a flag to, or they use a flag to turn things on and off. Instead of transferring the data itself to print, it transfers whether it can turn on or off. So, and that atomic bool, that works on all platforms. So that's 2 problems solved that were there before.
Okay.
So now for the fun thing, like where's the 1 + 1 = 2 kind of thing that I learned here, which isn't even that important for this to work because it's not needed for it to work. So if we have something to write into, then we create a thread like before, but we pass the trigger as weak reference, and the weak reference is non-owning. So if the throttle writer goes out of scope, that trigger boolean will also be destroyed. It will go out of scope too. So now with a weak pointer or a weak reference, we will not artificially keep that boolean alive in our thread, which really is just a worker thread. It has nothing to do if, there's no consumer anymore. And this is what is encoded with this system, and it's just a weak reference or a weak pointer. And it's something that I've used before, but never in Rust somehow. I've always used, arc clone to do that. So strong pointers that keep ownership alive. But with this, what you have to do, see here the 1 second sleep time again. And then what you have to do is, before use, you have to upgrade the pointer into an arc. So this upgrade function takes your weak pointer, your weak arc, and returns an arc potentially. It returns an arc only if that underlying resource is still alive. And as you have an arc yourself now, it definitely will stay alive as long as you hold that arc. So now you can use it safely. And as the T goes out of scope, the arc will release the strong binding, which means that potentially now the resource can go out of scope and stop being alive. And yes, once we have that flag, we can set it to true, and then we sleep again for the given duration. And that loop will naturally stop as the resource goes out of scope. So this thread will sanely shut down instead of just relying on the operating system to shut it down. We can now add stuff here safely, and we know this will not do ever anything wrong. It will not race. Yeah, I mean, maybe it still kind of races a little bit because the main thread might be just about to shut that resource down, and then the other thread comes and keeps it alive for just a little longer. Then the main thread might go down, and that thread here might do one more thing that now kind of, might not be the right thing. But I think that's besides the point, because that one isn't even printing anymore. If that one was printing, it's still kind of potentially a bit icky, but it's so much better than before. And just this. And yeah, this realization made me change ProDash, made me adapt how Git Oxide uses its own progress rendering. And now I use a weak reference there as well, so that progress renderers don't keep their progress alive like they did before. So they can't just print too much. And I had to do all kinds of dances to work around this, and I wasn't even really aware, and now it's so much more simple to coordinate the actual work done with the rendering of the progress, for instance, which is very, very similar to here. This is just the most trivial example of what's actually happening, and what ProDash does is more complex, but ultimately it boils down to the same formula now. And that's pretty neat, just neat. And
that's pretty cool. So this weak reference is basically just a way to force you to check if a resource is still alive instead of just assuming that it is. Yes. And that's where this mechanism comes of. It can shut itself down if it doesn't exist anymore.
Yes. So it's weak ownership. You don't actually own it. You don't keep it alive with the weak pointer. And that's typical. That's a typical thing to avoid cycles. Sometimes when you have a graph of nodes, then if they both have strong pointers to each other, they keep each other alive, even though they're not really used by anybody else anymore. And then you use weak pointers to circumvent that, so that there is a sense of ownership or a hierarchy of ownership. usual thing, nothing new there, but I never used it like this. So in other words, binding a thread to the lifetime of another scope. That's the thing you can do easily with that. And I never thought about it. Never. So
neat.
Very, very simple. And yeah, let's just make this an episode before it takes too long, and maybe just do another one right after. But for now, I think that's a nice end of the first. Happy Monday, and hope to see you soon. Thanks for watching. Bye bye.
Bye bye.